Hello students. In this video, we're going to delve into the periodic classification of elements. Understanding how elements are organized in the periodic table is essential for grasping the foundations of chemistry. This classification not only helps us predict the properties of elements but also provides insights into their behavior during chemical reactions. Let's start with an early attempt to classify elements, known as Dobereiner's triads. In 1829, Johann Wolfgang Dobereiner, a German chemist, observed that certain groups of 3 elements shared similar chemical properties and had a distinct relationship in terms of their atomic masses. He called these groups triads. What was fascinating about these triads was that the atomic mass of the middle element was approximately the average of the other two. For instance, in the alkali metal triad, which includes lithium, sodium, and potassium, sodium's atomic mass is roughly the average of lithium and potassium. This pattern highlighted the periodicity of elements, although Dobereiner's classification had its limitations, as not all elements could be grouped into triads. Moving forward, we encounter Newland's law of octaves. In 1864, John Alexander Newlands, an English chemist, took a different approach by arranging elements in order of increasing atomic mass. He noticed that every 8th element had similar properties to the first, much like the notes in a musical octave. This observation led to the idea that the properties of elements repeat periodically. However, Newland's law was primarily applicable to lighter elements and did not accurately predict the properties of elements beyond calcium. Despite its limitations, Newland's work was significant in pushing forward the idea of periodicity in elements. Next, we explore Mendeleev's classification of elements, which was a major breakthrough in the development of the periodic table. Dmitry Mendeleev, a Russian chemist, proposed in 1869 that when elements are arranged by increasing atomic mass, their properties recur at regular intervals. This concept became known as the periodic law. Mendeleev's periodic table was structured into horizontal rows called periods and vertical columns called groups, where elements with similar properties were grouped together. What made Mendeleev's table particularly remarkable was his foresight to leave gaps for undiscovered elements, predicting their properties with astonishing accuracy. For example, he predicted the properties of elements like gallium and germanium, which were discovered later and fit perfectly into the gaps he had left. Although Mendeleev's table was revolutionary, it did have some drawbacks, such as the placement of isotopes in elements like cobalt and nickel, which didn't fit perfectly into his atomic mass arrangement. With the discovery of the atomic number, the modern periodic law was established. This law states that the properties of elements are a periodic function of their atomic numbers rather than their atomic masses. The modern periodic table, which we use today, arranges elements in order of increasing atomic number. This arrangement corrects the inconsistencies in Mendeleev's table and provides a more accurate reflection of the periodic trends. In the modern periodic table, elements are organized into 18 groups and 7 periods. Elements in the same group share similar chemical properties because they have the same number of valence electrons. As you move across a period, from left to right, the properties of elements gradually change. For instance, elements on the left side of the table are typically metals, while those on the right are non-metals. This gradual change is due to the increasing number of protons and electrons as we move across a period, which affects the atomic structure and, consequently, the chemical behavior of the elements. Let's discuss some trends in the modern periodic table. One of the most important trends is the variation in atomic size. As you move down a group, the atomic size increases because new electron shells are added. However, as you move across a period from left to right, the atomic size decreases due to the increasing nuclear charge, which pulls the electrons closer to the nucleus. Another trend is the metallic character of elements, which refers to an element's tendency to lose electrons. Metallic character increases as you move down a group and decreases as you move across a period. This trend explains why elements on the left side of the table, such as alkali metals, are highly reactive, while those on the right, like noble gases, are relatively inert. The valency of an element, which indicates its combining capacity, also follows a periodic trend. In a given group, the valency remains the same, while across a period, it first increases and then decreases. This variation is directly linked to the number of valence electrons, which determines how an element bonds with others. Additionally, the electronegativity of elements, or their ability to attract electrons, generally decreases as you move down a group and increases across a period. Non-metals, particularly those on the upper right of the periodic table, are more electronegative than metals, which are found on the lower left. These periodic trends are crucial for predicting the chemical behavior of elements and their compounds. Understanding these trends helps us make sense of the vast array of chemical reactions that occur in nature and in the laboratory. Now, here's a question for you to test your knowledge. What is the name of the law that states the properties of elements are a periodic function of their atomic numbers? Please share your answer in the comments. The complete curriculum for Class 10 is available on our channel. Check out all the links provided in the description below. Please make sure to like, share, and comment for more such videos.